given a wave function psi, the probability density can be defined as psi star psi, and for a charged particle, psi star psi is its charge density. It's proportional to its charge density. I can just write charge q into psi star psi, that will be the charge density. So for a traveling wave, it's just rho equal to 1, because I have e power ikx and rho equal to 1. But for the two standing wave solutions we just saw at the zone boundaries, the psi plus wave function would give a sine squared kind of probability density, and the psi plus wave function would give a cos squared kind of function. And if I place that on a one-dimensional lattice with the ions shown here, and the spacing, lattice spacing is a, you can see that the psi minus wave function has got probability density peaks in between the ions, and the psi plus wave function has got probability densities peaks on the site of the ions. Now if an electron sits here, then it's closer to the ion, and therefore the attraction will be more, and therefore the energy would be lower, because it's an attractive potential, so the energy will be lower. Whereas if the electron sits here in between the ions, then the attractive potential would be less, and therefore the energy would be higher, the potential energy would be higher. So you can see that there are two distinct energy states, as it turns out, one in between the two ions and one on the site of the ions. Now this is fundamentally related to the existence of energy bands in solids, as we shall see. Now let's write this expression for the Schrodinger equation in momentum space, and we are going to solve this at the zone boundary. So what we are going to do is to assume that the periodic potential plays a role only at the zone boundaries, and everywhere else it's basically the electron is free. So that's called the nearly free electron approximation. So the effect of the lattice site is seen only at the zone boundaries. So we're going to solve this at the zone boundary. So we're going to only look for solutions with the wave vector equal to half the reciprocal lattice vector, or minus half the reciprocal lattice vector. And therefore in the Schrodinger equation, we are only going to retain the coefficient Ck, which is C capital K by 2 and C minus capital K by 2. And we will set this guy here as lambda, and this is exactly equal to the wave vector being equal to half the reciprocal lattice vector. So now, given this, I can now write down the two forms of the Schrodinger equation for capital K by 2 and minus capital K by 2. So if I set the wave vector equal to capital K by 2, then there is this Ck here, Ck minus capital K here, and that can be written as minus K by 2, because I can take this and shift it by minus capital K, and that will become minus capital K by 2, and I'll get this equation. And for the other equation, where the wave vector is equal to minus capital K by 2, I can shift it by plus capital K, and that will give me capital K by 2, and therefore I have written this coefficient as C capital K by 2. So that's why I have these four coefficients. So I look at only those terms with these two kind of coefficients. I retain only that in the summation, and I don't include any other term, because I'm doing the solution at the zone boundary. Please write it down once and see, and then you will be able to understand it much better. So immediately I have these two equations now. The only way for these equations to have a solution is for this determinant to vanish, and I can immediately write this, and my solution at the zone boundary can be written as lambda plus or minus u, and that's where you can see that the periodic potential sits. So I have now simplified it. I have not mentioned it before, but in the Schrodinger equation I've just simplified it that all those uk's are the same, and I've just taken the same u. So at the zone boundary, the energy does not have the form of simple free electron, it now has two values, lambda plus u and lambda minus u, and the corresponding wave function for this you can easily show to be this, which is basically a set of traveling waves, a set of standing waves, excuse me. So that's the solution at the zone boundary, exactly at the zone boundary, and those are the two standing waves I have just mentioned with the different charge densities. Now you can do the same calculation for wave vectors near the zone boundaries, but not exactly at the zone boundary, but near the zone boundary. So again, from the form of the Schrodinger equation, you can write down the two expressions for lambda k and lambda k minus a reciprocal lattice vector. You make sure that you retain only ck and ck minus capital K only in the summation, so that you get this form for the two equations. Again, you can solve, you have to solve for this determinant. Please solve and show that you'll get a quadratic, find the two roots, and please do that exercise, and you will show that you will be able to see that as the electronic wave vector approaches the zone boundary, there are two solutions. So away from the zone boundary, you can consider the electron as a free electron or a nearly free electron, and this form of the band, energy band, that is the energy dependence with respect to wave vector, resembles that of a free electron here. But as the wave vector approaches the zone boundary on both sides, then because of this constraint, the energy has got two roots. So you have one value here, and for the same value of the wave vector, you have another value of the energy and no other value in between. That's where you get the band gaps. So you have a band here, and that band is not continuous. Now there is a gap at the zone boundary, and that's where you have this concept of band gaps in semiconductors, insulators, and so on. But we have done it for the simple one-dimensional case to show how it comes. It comes because band gaps in solid comes because the electronic wave functions can get Bragg reflected at the zone boundaries in the reciprocal lattice of the first Brillouin zone, second Brillouin zone, etc. On all the zone boundaries, there is Bragg reflection of the electronic wave function, and because of this Bragg reflection, there are traveling wave solutions become standing wave solutions at the zone boundary and near the zone boundary, and because of that, for a same value of the electronic wave vector, you get two solutions and of the energy, and therefore only two solutions, one is A and one is B, and nothing in between, and therefore what was continuous function for all other k values now there is a band gap, and there are discrete solutions at the zone boundaries because of Bragg reflection. That is the origin of band gaps in a solid. So so I can now extend this Bragg reflection for all other zones. So this is the first Brillouin zone. You have this band gap here. Then in the next zone you have the band gap here and here. Third zone you have here, and so on. You can see what used to be a nice free parabola now has become clipped in various places, and now you have segments because of the periodic potential. And like I said before, this is called the extended zone scheme. Zone scheme. Excuse me. I can reduce this extended zone scheme by taking this segment here and pushing it inside. This segment I can push it here. This segment I can push it here. This segment I can push it here, and so on. So I can fold it all inside, and the extended scheme becomes a reduced zone scheme. Another way of depicting is you take the extended scheme and you keep so you have this this function here. You keep drawing that. You extend this out in all the zones. You take this function, you extend it like that. You take this function, you extend the wave in all the zones like this. Take this guy and extend it, and so you get all this. Again, now you can see the band gap here. You can see the band gap here, and so on. So that's one more way of depicting it. You can do whatever you want. That's just they're all the same. Now, it's important to understand that suppose there are n primitive cells. We had seen that for n primitive cells, inside the first Brillouin zone, there will be n k points. Now each band will have nk points. So this band, this is the first band that will have nk points, this is the second band that will have nk points. Now each k point has the same energy for upspin and downspin, so it is doubly degenerate. So therefore you have 2n electronic states or 2n k states in each band. Because of the double degeneracy, you have to multiply by 2, so you have 2n k states in each band for you to fill electrons. So now suppose there is one atom per primitive cell, and that one atom gives you one valence electron like sodium. Then you can, if you start filling, there are 2n states for you to fill, but there is only there are n primitive cells. Only one electron comes from each primitive cell. So out of these 2n states, only n will be filled. Therefore the band will be half filled. So given this band, there's one energy band like this, and that band will this has got 2n electronic states for you to fill, but only n states is filled, and you can see the band will now be half filled. Now at t equal to 0, this is the highest occupied energy, and that will be the Fermi level. Now if you were to apply an electric field, the electrons near the Fermi level will get excited, will acquire a momentum because of this electric field. But since there are empty states, the electrons which are excited by the electric field can travel into these empty states, and you can get a current. That is why you that is why you call this a metal, because they are able to conduct the electricity, and because there are empty states above which are unfilled, and you can get electrical conduction. On the other hand, you can have situations where like one band is filled, and then there is some space for one band is filled, and the next from the next band you can have it's only about half is filled, or quarter is filled, or whatever. Again, this also is a metal, because this can conduct happily in these empty zones, empty states here. Another example is, you have one atom per primitive cell, and each atom has got 2 valence electrons. So what happens is, you have 2n electronic states in each band, but because 2 electrons are there in for each atom as valence electron, all the 2n states will be filled, and now the band will be fully filled. Suppose the band is fully filled, if you apply an electric field, as long as a small electric field, you can't apply an electric field that destroys the solid itself. It's a very small electric field. You can try to it will try to push the electrons. The electrons have no empty states, and therefore they will not acquire the momentum. There is no, they cannot go into any state above this. Like in this case there are empty states. So if you apply an electric field, the electrons will get a momentum, and they can travel into these empty states and create a current. But all the states in this band are filled, and there can be no current generated, and that's why you have an insulator. And you can see that this band is fully filled, the other band is fully empty, but there is an energy band gap. There's a if the band gap is very large, then you call that insulator, it becomes a proper insulator. If the band gap is small, then if you heat the system, then there may be a few electrons that get excited from here to there, and those electrons can conduct, and you have something called a semiconductor. Of course, then you in addition, you can dope the semiconductor, increase the carriers, and do all those kind of gymnastics. But in general, this is the classification. You have a metal where the states are not fully filled, and you have an insulator where the state is where the band is fully filled. Or there's another situation also, when suppose there are 2 atoms per primitive cell, and each atom gives you contributes 1 valence electron. Then also all the 2n states will be fully filled. Then also you will get an insulator. But in certain cases, what happens is, this higher band here overlaps in energy with the lower band. So if you can start filling the states, and some of these states can also get occupied here because they have the same energy. And you can see there's a very small space here. Just a few states in the lower band are empty, because some of the states are taken by the higher band which overlaps with the lower band, and that's called a semi-metal, because it has got a few states, few empty states for the accelerated electrons, because the electric field will create an acceleration. It is a few states for the accelerated electrons to travel in, and that's called a semi-metal. Its resistivity will be much higher, that on the conduction will be much lower than that of a metal. So examples are the alkali metals and noble metals. They have one valence electron per primitive cell, so their bands will be, the lower band will be half filled, the lowermost band will be half filled, so they have their nice simple metals. In the case of alkali earth metals, they have two valence electrons per primitive cell. They could be insulators, but there is a band overlap like I just showed you, and therefore you get semi-metals. Diamond, silicon, germanium, etc. They have two atoms, and each atom contributes 4 electrons. So you have 8 electrons per primitive cell, and that's again the band will be fully filled, and the bands don't overlap. So a very simple simple formula that doesn't work all the time is, thumb rule is, even number of valence electrons, even number of valence electrons would lead to a insulator in the case where there is no band overlap, and odd number of electrons would lead to a metal. That's a very simple thumb rule. It doesn't work all the time, but just for easy understanding.